Hello everyone and welcome to our session. I'm Dr. Eris, and today we are going to dive into the foundational concepts of machine learning by building a linear regression model from the ground up. At its core, linear regression is about modeling the relationship between a dependent variable and an independent one. It allows us to predict outcomes based on historical data patterns. Take a look at this equation. Here, y is our target, beta 0 is the intercept, and beta 1 is the slope that represents the weight of our input x. Our goal is to find the best values for these coefficients. In this class, we are taking a first principles approach. We will avoid libraries like NumPy to ensure you internalize the logic of the algorithm by constructing it yourself. Our journey today follows this roadmap. We'll start with the mathematical theory, move into algorithmic design, and finally implement a working Python script from scratch. By the end of this session, you'll have a fully functional prediction tool that you built entirely on your own. Let's get started with the math. Now that we've set the stage, let's dive into the mathematical framework that powers linear regression. While it might look like simple algebra, this equation is the engine of our prediction model. You are likely familiar with the standard line equation, y equals mx plus b. In the context of machine learning, we use this to map a relationship between our known data and our desired output. First, we have y, our prediction. In statistical terms, we call this the dependent variable because its value depends on the inputs we provide. Next is x, the input feature. This represents the data we already have. For example, the square footage of a house if we are trying to predict its price. Then we have m, the slope. In our code, we'll often refer to this as the weight. It determines how much influence the input x has on our final prediction. And finally, b is the intercept, or the bias. This allows our model to have a baseline value even when the input x is 0. The ultimate goal of our algorithm is to optimize these two values, m and b, to ensure our prediction error is as small as possible. Before we move on to the visualization, let's think about how these components interact. In linear regression, our goal is to find the line that best fits these data points. Let's explore how changing the parameters affects the model. The slope slider rotates the line. Notice how it changes the direction of the trend relative to the data points. The intercept slider shifts the entire line vertically. This represents the starting value when the horizontal variable is 0. A slope of 0 results in a horizontal line, meaning our model predicts a constant value regardless of the input features. By adjusting both parameters, we can find an optimal fit that minimizes the distances or residuals between the points and the line. The objective is to minimize the mean squared error, MSE. While we are doing this manually here, algorithms like gradient descent automate this process. Building on what we just covered regarding the best fit line, we need a rigorous mathematical way to evaluate our model's performance. This is where the mean squared error, or MSE, becomes our primary tool for measuring accuracy. We define this using a cost function. In machine learning, this function acts as a quantitative measure of the total error. It essentially tells us how unsuccessful our parameters are at predicting the target values. Our ultimate goal is to minimize this value. To compute the total cost, we first look at individual data points. The residual is the simple distance between the actual observed value and the value predicted by our linear equation. It's the error for a single point. Here is the formal calculation for mean squared error. We take every residual, square it, sum them up, and then divide by the number of observations. N, this gives us the average of the squared distances. You might wonder why we square these numbers. Primarily, squaring ensures all errors are non-negative, so they don't cancel each other out. Additionally, it more heavily penalizes larger errors, which forces our model to pay more attention to outliers. Now that we've defined the mean squared error on the previous page to measure our model's performance, the next step is figuring out how to actually improve it. This brings us to the core of machine learning, optimization via gradient descent. To understand gradient descent, visualize yourself standing on a foggy mountain, the error hill. You can't see the bottom, but you can feel the slope under your feet. To get to the valley, you'd logically take a step in the direction where the ground slopes downward most steeply. In our model, this translates to iterative parameter updates. Instead of solving for the best fit in one giant leap, we make small calculated adjustments to our weights and biases to slowly reduce that cost function we just calculated. Mathematically, we use this update rule. Here, W represents our weight, and the gradient tells us the direction of the steepest ascent. We subtract it to move downhill. Notice the symbol eta. That is our learning rate, which controls the size of each step we take. Choosing the right learning rate is a balancing act. If your steps are too large, you might overshoot the bottom entirely. If they're too small, it will take forever to reach the minimum. Our goal is to navigate this cost surface efficiently until we reach the global minimum shown here. By visualizing the path toward the global minimum, we can see how the model learns over time. This iterative process is what allows our linear regression model to eventually find the line that best fits the data we provide. Building on the mathematical foundations we just established, we are now ready to translate those concepts into Python code. To truly grasp the first principles of data science, we will avoid high-level libraries for a moment and focus on how data is handled at its most basic level. For our dataset representation, we'll utilize Python's native lists to build our feature matrices. Lists provide the flexibility we need for iteration, while tuples are ideal for immutable data points that should remain constant throughout the training process. One critical step before we jump into the model is scaling. As we saw in our previous discussion on gradient descent, if your features have wildly different scales, the cost function becomes elongated, making it difficult for our optimization algorithm to converge smoothly. This formula represents min-max normalization. By transforming each value relative to the minimum and maximum of the dataset, we ensure all inputs fall within a 0 to 1 range. This parity is essential for maintaining gradient stability during the learning process. Our implementation logic will be straightforward. We will iterate through our feature columns, calculate these bounds, and apply the transformation. Maya. This manual approach will give you a clear view of how every single data point is processed before the model ever sees it. Before we move to the final project, let's consider the trade-offs of this manual approach. Now that we have covered the necessary data structures in pure Python, it is time to put everything into practice with our main project, implementing the model. Our goal is to develop a complete linear regression script from scratch, handling parameter initialization, the training loop, and final validation without any external libraries. To help you succeed, Dr. Eris will oversee the mathematical rigor of the gradient descent, while Clara provides support for implementation details. Leo and Maya are also available to help explore the conceptual why and ensure our code remains organized and testable. Please select a role and let's begin the implementation. Now that we have completed the manual implementation in Python, we must verify if our model actually works. This testing phase is where we confirm our gradient descent logic was sound. First, let's look at numerical validation. We need to monitor the loss curve throughout the training process. A successful model should show a consistent decrease in error. As we covered earlier on page 4, we use the mean squared error formula to quantify our success. By comparing the initial MSE with the final value after our iterations, we can mathematically prove that the model has learned to better fit the data. However, numbers don't tell the whole story. We also need geometric intuition. We should overlay our final regression line on the original scatter data to visually inspect if it follows the general trend. Lastly, let's acknowledge the library realities. While building this from scratch is vital for understanding the why behind the math, in a professional setting, you'll likely use optimized tools like scikit-learn for efficiency and scalability.